Now, I will be solving one question from the Civil Services examination. The question is as follows. Use the following data to determine the normal boiling point of mercury and what assumptions must you take me in order to do the calculations. Data given is like this. Mercury liquid state, delta HF naught is equal to 0. S naught is equal to 77.4 joule per Kelvin mole. Mercury in the gaseous state, for mercury in the gaseous state, delta HF naught is equal to 60.78 kilojoule per mole and S naught is equal to 174.7 joule per Kelvin mole. Here, naught, which is written here, delta HF naught, S naught, the naught is showing the standard state, mercury in the standard state. That is at 1 atmospheric pressure and 225 degrees Celsius room temperature and in the at the unit activities. So these are the standard state in which the delta HF naught, that is the heat of formation of mercury in the liquid state, is given to be equal to 0, and S naught, that is entropy in the standard state of the liquid mercury, is 77.4. Similarly, and for mercury in the gaseous state, delta HF naught is equal to 60.78 kilojoule per mole, and entropy in the standard state of the mercury in gas phase is equal to 174.7 joule per Kelvin mole. So there is change of phase when the mercury is heated. When from it changes its phase from liquid state to the vapor state, and during this, when it reaches the equilibrium condition, that is on raising the temperature of mercury, it reaches a temperature when there is an equilibrium existing between the liquid state and the vapor state. That is the amount of mercury changing from liquid state to gaseous state is same as the amount changing from gaseous state to the liquid state. So there is the solution. So in the solution, uh, it is shown that phase transition of mercury occurs from liquid state to the gaseous state. When mercury in liquid state is heated, it reaches a temperature at which the liquid and gas phases are in equilibrium. So equilibrium is attained, then that temperature, the corresponding temperature at which the equilibrium is attained, that is called the boiling point of mercury. So the phase changes like this: mercury in liquid state to mercury in gaseous state. At equilibrium, standard free energy change delta G naught is equal to 0. And but delta G naught is equal to delta H naught of vaporization minus T delta S naught of vaporization. So as because we know that delta G is equal to delta H minus T delta S, and delta G naught is equal to delta H naught minus T delta S naught. So in the vapor phases, this will this equation will be applied, where delta H of vaporization, that is equal to standard enthalpy of vaporization. And to find out it value of this delta H naught of vaporization, we have to subtract the delta HF naught of mercury in gaseous state. Uh, and from this, we have to subtract delta HF naught of mercury in liquid state. Only heat of formation of mercury on the standard state in the gas phase minus heat of formation of mercury in the liquid state. So that data is given in the question itself. It's given that delta HF naught is 60.78 in the gaseous state. So that is to be applied here. And we are getting 60.78 minus 0 kilojoule per mole. And that comes out to be equal to 60.78 kilojoule per mole. And that is equal to 60.78 into 10 to the power 3 joule per mole. Changing kilo to kilojoule to joule. Now, standard entropy of vaporization. To find out the standard entropy of vaporization, delta S naught of vaporization is equal to S naught of mercury in gaseous state minus S naught of mercury in liquid state. And both the values are given in the question itself. So that is 174.7 and 77.0. So we will apply these values here and we are getting 174.7 minus 77.4 joule per Kelvin mole. That is equal to 97.3 joule per Kelvin mole. So at the boiling point of mercury, delta G naught is equal to 0. It means that delta H naught of vaporization minus T delta S naught of vaporization is equal to 0. From this equation, we see that T temperature is equal to delta H naught of vaporization by delta S naught of vaporization. And putting the values of these two terms, we are getting that is equal to 60.78 in 10 power 3. We have calculated it here itself, 60.78 like this. And then delta S naught of vaporization 97.3. Both the values are taken from the earlier calculations. And then we will solve it. Then we will get 60780 divided by 97.3. That comes out to be equal to 624.7 Kelvin. To change the temperature, we are getting the boiling point this in the Kelvin scale. But if we want to change it to the degree Celsius, we have to subtract 273 from this. So subtracting 273, we are getting 351.7 degrees Celsius. Hence, the required boiling point is equal to 351.7 degrees Celsius. And this is the answer of this problem.